Welcome back everyone to our calc series. Today we are covering the chain rule, which is, I would say, the first part of BC Calc that starts getting a little bit more complicated. And what this is that it's fundamentally a very powerful rule that can help you find derivatives for a broader range of functions. So this is the chain rule. So let's say we had this f of g of x, this composite function, and we wanted to take the derivative of this whole thing. And the chain rule states that this would be equal to f prime of g of x, so f prime of what's in there, times g prime of x. And uh, my preferred version of the chain rule is this Leibniz way of writing it, Leibniz, because it really shows how this chain rule works intuitively. So we haven't talked about this notation much before, so I'm going to introduce this here real quick. So d over dx of f of x just means the derivative of f with respect to x, right? So this is what we said was equivalent in our derivative introduction video. And so what we're doing here is we're taking d over dx of y, right? So dy over dx is equal to means d over dx of y. And it says that it's equal to d over dt of y times d over dx of t. And so really what this shows is that it makes it more clear that we are differentiating with respect to this variable. So like with f prime of x, we are implicitly differentiating with respect to x, right? So for example, if I had f of x is equal to x cubed, and I asked for f prime of x, everything would be about x, right? Like this. Then here, sort of what we're doing is like we have, for example, y of t, right? And we're taking this with respect to t. And here we have t of x, and we're taking this with respect to x. And here we have y of x. So ultimately, what we're doing is we have y equals f of g of x, and we're letting t be equal to this. And we're basically saying this. So like, I want to find the derivative of y with respect to x. And this should be equal to the derivative. We're first going to find how rapidly y changes with respect to this t. So this is dy over dt, right? So like how fast y changes with respect to t. And then we're going to figure out how quickly t changes with respect to x. Then if you multiply these two rates, then you would find how quickly y changes with respect to x. So sort of it's like you have these two rates. So let's say you have how fast A is compared to B and how B is compared to C. Then you can use this to figure out how quickly A changes uh, with respect to C. So this is the idea of chain rule. And if you're really struggling with this notation, you can first just use this version because we're going to use this in the next problems. And you're going to see how this works in the problems just algebraically and numerically. And maybe later it'll consolidate. So using the chain rule, we're going to find the derivatives for the following examples. So first of all, for this example, one good way to start for the chain rule is if you're just beginning with learning the chain rule, it's good to start identifying what the functions are. So for example, you would first see that the outer layer, f of x, is this sign, and that g of x is this 2x plus 1. So then if this were put together, then we would have y equals f of g of x, and that would indeed be sine of 2x plus 1. So now we can apply the chain rule, and we would find that since y is equal to f g of x, then we would have dy over dx, or which is just y prime, is equal to f prime at gx times g prime of x. So then here, this f prime of x, so f prime, this function f prime of x, as covered in our trig video, is cosine x, while g prime of x here is equal to 2. So here we could just plug in g of x into this cosine. So this would become f prime, so f prime of x is cosine of evaluated at g of x, which is 2x plus 1. And then you multiply this with the g prime, which is just 2. So the answer is 2 cosine 2x plus 1. If this feels a little bit weird, it's fine because we're going to cover a lot more examples. And before this next example, I'd actually like to cover a general derivative, and that is a to the x. So last time we did cover what e to the x is, but we did not cover what it is for a general a to the x for a is greater than 0. So this is what we're going to do this time. So dy over dx we want to find. And again, we're going to apply the chain rule. We can rewrite this as e to the ln a to the x. And this could be rewritten as e to the x to the ln a. So then we can let f of x be equal to x to the ln a. We can let g of x be equal to e to the x. So then g prime of x is equal to e to the x. And f prime of x is equal to ln a x to the ln a minus 1 by the power rule. So then we can start plugging things in. So this is f prime. F prime is ln a, and then x to the ln a minus 1. And then inside we're going to put in g of x, right? So f prime, so if you look here, f prime g of x. So this is f prime, and then we're going to put g of x in here. And then this we're going to multiply with g prime x, which is just e to the x. So then we can algebraically manipulate this. So there's going to be ln a, and then we're going to find this is e to the x ln a minus x, but then here we have plus x, so this cancels out. And we would have, well, you can put this ln a back with the e, right? So you can rewrite this as ln a e to the ln a to the x. And this would become ln a to the x, like this. So this is the derivative of a general a to the x. So then we can apply this right over here. So here we can define f of x is equal to a to the x, or like 5 to the x, rather. And g of x is equal to x squared plus 1. So then we can evaluate dy over dx again. dy over dx is just f prime g of x times g prime of x. So let's evaluate f prime of x. F prime of x is ln 5 times 5 to the x. And g of x, g prime of x is equal to 2x. So then we can plug in the values, or like the expressions. F prime is ln 5 times 5 to the x, but then this x would become g of x. So g of x is x squared plus 1. And then we're going to multiply this to g prime of x, which is 2x. So this here is our derivative. Right. So at this point, if I were to summarize a general procedure, it would be to first write out the composite functions, write out f and g. Then 2, you would want to compute f prime g prime, and then 3, and you just plug into the formula, or like you plug in to this chain rule right over here. So here we have our last example of this part. Here we can let f of x be equal to log 3 of x, and let gx be equal to sine x. So then again, this is f gx. And then we can find the derivative of f of x. So notice f of x is actually, this is actually equal to log 3 is, log with base 3 is actually equal to ln x over ln 3. And then ln 3 would become a constant, right? So f prime of x we can write as, well, this is a constant, right? So we can take out the constant. And then the derivative of ln x is equal to 1 over x. Then g prime of x is just equal to cosine x, right? Like this. So then dy over dx we can evaluate as f prime of x, f prime g of x times g prime of x. And that is equal to f prime is 1 over ln 3, 1 over g of x, sine x. And then we're going to multiply this with g prime of x, which is cosine x. Or alternatively, you can write this as cotangent 3, like this. Okay, so find the slope of the tangent line to the curve y at x equals 0 by expanding the expression. So again, if you want the slope of the tangent line, this is exactly what the derivative does. So we want the derivative at x equals 0. And we first want to try it by expanding the expression. So expanding, we would find y equals 16x to the fourth plus 32x cubed plus 24x squared plus 8x plus 1. And that's a lot of expanding. But then you would want to find the derivative. So dy over dx you can find is equal to 64x cubed plus 96x squared plus 48x plus 8. And then 1 disappears. And then you can evaluate this at x equals 0. So you can write, one way you could write this in terms of notation, it's dy over dx evaluated at x equals 0. So if you put this vertical bar here, it means evaluated at x equals 0. This should be equal to just 8 because everything else disappears, right? So dy over dx is equal to 8. So this one is relatively easier because it's x equals 0. But if you had something that's not x equals 0, if it's x equals a for a is not equal to 0, then it would be a lot of computation. So on the other hand, we have the chain rule. So here we can note that we can let f of x be equal to x to the fourth and g of x be equal to 2x plus 1. So then f prime is equal to 4x cubed and g prime is equal to 2. So then here with the chain rule, we can find dy over dx is equal to f prime g times g of x, g prime of x. And that would be, so here we have 4x cubed, so x cubed times g prime of x. So just like this. Then immediately we can just plug in x equals 0. So dy over dx at x equals 0 is equal to 4 times 2 times 0 plus 1 cubed times 2, and that's equal to 8. So here we just showed two different ways of finding the derivative, and evidently the chain rule seems to be faster because if you had something that has even greater power, let's say this was something like 7 or 8 or 9, then it would be insane to compute with expanding. Okay, so given the charts of f and g, find the derivative for each of the following. So on the FRQ, we have a lot of similar problems like this where they give you a table of values and sometimes derivatives can be a part of them. So this is sort of like a question type. And the general trick for this is that because you don't know the exact functions, you would have to sort of evaluate the derivative earlier than you would typically do. So for example, let's take a look at this first one. We're going to define h of x to be x over 2. And then this f of x over 2 would just become f of h of x. And we're going to let this be y. So we want dy over dx, right? This original thing, dy over dx. And that is equal to f prime of h of x. Notice it's still the chain rule. I've just switched g with h because g is used up here. And what we're going to do here instead is we're going to directly evaluate dy over dx at x equals 1. Rather than computing, because usually we would find this is something in terms of x, and then we plug in x equals 1. But we don't know the exact functions of f. We do know h, but we don't know f, right? So here we're just going to directly plug in. This is going to be equal to f prime of h of 1 times h prime of 1. And that is equal to h of 1 is 1/2, and h prime is equal to 1/2. So this is going to be f prime of 1/2 times 1/2, and f prime of 1/2 is -3. So this is -3 over 2, like this. And one mistake people commonly make is that they would directly write something like, let's say, dy over dx equals f prime h1 times h prime of 1. And the problem with this is that dy over dx is just y prime, or like it is the derivative of a function. And this function we're saying here is equal to this. And this, when you evaluate out, is a constant, right? Because here you're plugging in a specific value. And basically, then you're saying a function is equal to a constant. And this is an invalid way of writing your notation. And instead, what you should do is whenever you have the 1, you should make it clear that this is at x equals 1. This is a particular instance of this derivative function. It is not what it is all the time. For this next one, we would find, we can just write this as f prime of g of x times g prime of x evaluated at x equals 0.5. And this is equal to, so g of x is 1 and f prime of 1 is -4. -4 times g prime of 0.5, that's 0.5. So this is equal to -2. Then this one is equal to f prime g, I'm just going to abbreviate dx, g prime f over g squared evaluated at x equals 1. And this should be equal to, well, f prime at 1 is -4. G at 1 is 7 minus g prime, -1, times f at 1, 2, over g squared, which is 7 squared. And this is equal to -28 plus 2, -26 over 49, like this. Then here finally we have a difference of squares, weirdly, and the derivative of this, so we want d over dx of this whole thing, it should be equal to, so if you consider the outer function as something squared, then this would become 2 times this something, and then times the derivative of what's in there. So I'm still using the chain rule, but a little bit more faster. And then 2g of x times g prime of x. So if you practice more with the chain rule, you'll start recognizing patterns and it'll become faster. So again, it's all about practice. So here we have this expression right over here, and then we're going to choose to take dy, so we're going to let this be y then. Dy over dx evaluated at x equals 0.5. This is equal to 2 times all these things. So 2 times f of 0.5, that's 1. F prime, that's -3, minus 2 times g and g prime at 0.5. So that's 1 and 0.5. So this is equal to -1 minus 7. So then we have some harder examples. I'm just going to write out the answer so you have answers for your own practice. Please try them if you still feel like you're not fast enough at the chain rule. Practice is the key thing for derivatives. Like this. So these are all the answers. And finally, we have, if g is the inverse of f, then we want to show that this here is true. We could notice here that this looks like one of the factors from the product rule, and this also. So actually, if we write everything together, we would find this is exactly what or actually like this is g and f reverse, but like this is what the chain rule would state. So this would motivate us to consider g of f of x, this function. And this should be equal to x itself because g is the inverse of f. So then we can take the derivatives of both sides. And then we would obtain g prime f of x by the chain rule, f prime of x is equal to 1. And so hence we have this expression right over here. This is also some foreshadowing for what's going to happen in the next video. Notice we still haven't completely established this method yet, and this is exactly what we're going to cover in implicit differentiation. Thank you everyone for this video.